Hey everybody, it's Tony from Adafruit, and I wanted to do a follow-up stream on using MicroPython with the ESP8266 Wi-Fi microcontroller. So last week, a week ago from today, I did a stream on just the current state of MicroPython and how to compile it and load it on the ESP8266, and just kind of touch the surface of a few things you could do with it, like turn on an LED, turn it off, some basic stuff. And since then I saw there's some great documentation for the project, and I should preface this all by just saying that this is all in development stuff. So they had a great Kickstarter maybe a month or two ago, really well funded, and so there's all kinds of cool new features they're adding, and they're doing all the development on GitHub, so it's in the open, so you can pull down the code. So this isn't a final product. It's still a project that's in progress. But I just wanted to check in on it again and just play with a few different things that they have. I noticed there's some cool stuff that it supports. So it can do things like control Neopixel LEDs. There's some Wi-Fi support that we can play around with a little bit, and a little bit better GPIO support. So I even noticed there's like PWM support, so you can like dim an LED or maybe even play tones on a speaker. So really cool stuff, and it's all with the Python programming language running directly on the little ESP8266 Wi-Fi microcontroller. So real nice little platform. So let's just kind of jump in, and I'll show you what I've got here to show off. And so it'll probably be a little quick stream, maybe about 30 minutes or so. And so let's go to the desktop view here. Oops, turn that on and go here. So okay, cool. So on the desktop, we'll go through, and I'll put a link in the description below to this web page. But this is, from what I've seen, appears to be the documentation for ESP8266 MicroPython. And it's really well done so far. I mean, it has good little examples of the code. And remember, it's all work in progress, so you'll see there's some bugs and things. Not everything's complete, but it's cool to see what they have. And then in the upper right up here, so this is, right here is the Feather Ascii ESP8266. And I mentioned in the previous stream, which by the way I'll put a link in the description below also if you want to watch the first video. But real nice, easy way to get started with the ESP boards. But any of the ESP little modules you can use. So even if you just have the little $2 or $3 one, you can load it up. A little more painful to use. You're going to need a serial to USB converter, and the pinout is a little funky with those chips. Versus the Ascii is nice in that it's got the serial to USB built in. Nice little form factor here. All the pins are broken out from it, so easy to get started with. Now I have it hooked up to a little breadboard here, and I have an LED. This is connected to pin 2, and it just so happens it's on by default. But we'll see if we can control this. And then I have a little Neopixel ring right here. This is a 16 pixel Neopixel ring, and it's just connected up the power. So it's got 5 volts coming from the VUSB voltage source. So this is just the USB bus voltage that's powering the Neopixels, and then the signal wire is going into pin 15 on here, and so we'll be able to control this with MicroPython. And so I won't go through the whole process again of like how to compile MicroPython. Go back to the first video if you're curious how to compile it and load it. It's really easy, even if you're on a Windows machine, or Mac, and you've never set up a cross compiler before. I have a little guide in the first video I linked to where you can use Vagrant and VirtualBox to make a little Linux machine, and then that'll do the compilation and the cross compilation, and you just have to run a few commands. It's not crazy at all. And you do want to compile it because this is changing very quickly. So every few days there are new commits, new things coming in. So you want to make sure you get the latest code for this. Now I've already pulled down the GitHub repository. I've synced it. I've made it up to date. I've built the latest firmware, and I flashed it to my ESP board already. So it's running the latest firmware. So let's just connect and let's start playing with some of the different functions they talk about in the documentation here. So I'm going to connect to the serial port that this device shows up as. So it's on my Mac. It's dev tty .slab to USB to UART, and then 115200 is the baud that MicroPython has. And when you first connect, this will give you the little Python console, and you probably want to hit enter just so you can see the input here, the little cursor. And then it's normal Python just like you saw before. You can do print statements. Lots of Python is implemented in here, like the basic syntax, the data structures as far as like dictionaries and arrays and things like that. It's all there. It feels just like Python. A lot of libraries are implemented, and we'll see some of those here. So let's just kind of dive in, and I'll just kind of go through this quick reference real quickly and just kind of mention some of the modules here that they have implemented so far, and we can try out a few things here. They mentioned the machine module, which is kind of interesting. So it looks like this one gives you access to some of the ESP's hardware. And like I mentioned in the previous stream, a useful command is the dir command. So you can run that on an object. You can actually just run it alone, and this will tell you everything in the global namespace. So these are things that I could access, and then if I run it against like a module like machine, it'll tell me everything inside the module that I could access. So you can see the machine module has all kinds of stuff in here, like for UARTs, I2C, SPI access, that kind of stuff. Interesting, there's a mem8, mem16 command. I haven't seen these, but this probably lets you read memory for different, the current memory of the chip. But it looks like, so there's a frequency, so you can read, and actually, wow, so you can set the CPU frequency, so that's kind of cool. So now if I call this right now, it should just be 8 megahertz, because that's the default. Yeah, so you can see 80 million, or sorry, 80 megahertz, so 80 million. And that's just the frequency the chip runs at. I didn't realize, this is kind of cool. I guess you can change the frequency. I'm not going to do it because I don't want to make this unstable, but that's pretty cool that you can just have a script to overclock this stuff. And MicroPython itself, it's not doing any magic in the sense that, like, it's not doing something that you can't do with the ESP8266 SDK. MicroPython is just built on top of the ESP8266 SDK. So, I'm betting that SDK exposes functions to like set the clock frequency and stuff like that. But the nice thing with MicroPython is that it builds on top of that a whole Python infrastructure, and you'll see they've implemented some great, really useful libraries like Json parsing, stuff that's just a royal pain on Arduino, very easy in Python, and so you can see some of this stuff. There's also an ESP module. This one again has like some system level stuff that looks pretty useful. Now networking we'll come back to because this one's pretty cool. This is how you get access to Wi-Fi network and how you can talk to servers and things like that. But I ran into a few problems, and we'll see the error that I hit. And again, it's all beta stuff. It's kind of in progress. The time module. So this is like the Python time module, but not all the way filled out. But it does have the sleep function, which is really useful for delaying for a period of time. And I actually noticed they have sleep millisecond and sleep microsecond functions here. So those are kind of useful because the ESP8266 has a little real-time operating system internally, and so you don't want to sleep for a long time without giving that RTOS some cycles back to do what it needs to do. Like, it needs to take care of Wi-Fi. There's like certain asynchronous events to stay connected to the access point and to handle connections and things like that. And so the ESP, there's only one core on that chip, and so you don't have multiple cores. You can't just give one core to talk to the Wi-Fi radio and then another core to run your program. Maybe future chips like the ESP32 might be a little better about that. But because of that, you have to be careful. You can't just go into an infinite loop, or else the chip will reset itself. So it's useful to know here that you've got multiple sleep functions. The sleep function, the standard one in Python, it takes a floating point value. So let's see, if I import time, I can call time.sleep 0.05, and that'll sleep for 50 milliseconds, or like 0.05 seconds, and that's perfectly fine to do that too. So it's either way you want to do it. I'm guessing the sleep milliseconds and microseconds are maybe a little bit more efficient because I'm guessing they don't take like a floating point value, and so there's a little extra overhead to parse that and deal with that kind of a value. So this is kind of cool, and it looks like you can also get a counter of the current milliseconds, so that's really useful. Like if you're doing a main event loop and maybe you've got like some logic that you want to run at a certain frequency, and so you can see how much time has elapsed. So useful to see that inside of here. Also has a timer, which seems pretty cool. So this is it looks like just something you can set up to call a function at a certain period. So say like every 5 seconds here, you can call a callback function to like print something out or do some logic. So good to know that that exists. And that's another thing, you've got one core, and so you've got to make the most use of it. You don't have threads. Like, there's not a full operating system in here with a kernel and context switching and stuff like that. So at least the Python code doesn't expose anything like a thread to go run a task in the background. So a timer is kind of like, maybe a poor man's thread in some way, that if you want something to happen in the background, quote unquote, you could run a timer that will, kick at every certain, some frequency and run some of your logic. for that. So good to know about that. Now in the previous stream, I showed off how to access GPIO, and I was showing, excuse me, a different kind of way to do it. I was using this PYB, the PyBoard class, which is kind of not the right way to do it these days. It looks like with MicroPython, this machine class is kind of the right way to use GPIO. And so you can see you create a pin object, and you can create it as an input or an output. It's just like Arduino. And then you can set it if it's an output to like a high or a low value, or if it's an input, you can read the value in here. So for example, let's play with the little LED on the board. So this is connected to pin 2, and so I've already imported machine, so now I can create a pin, and I just want to create a, or here, let's call this LED pin, and we'll do machine.pin, and then you pass in the pin number, so that's pin 2 for this board. And then the type of pin this is, an input or an output. And so I want to do machine.pin.output. You can see it turns it off, so I'm guessing it was probably in some default, maybe high impedance state, like maybe it was set as an input, and maybe there's a pull-up on here. But for whatever reason, I put it into an output, and it set it down to a low level. But now let's just do LED_pin.high, and this will turn it on, so that's cool. And then LED pin dot low turns it off, so it works just the way you expect it. So real similar to what I showed in the last stream, but look for the machine class module rather now, and it has the pin class that's just like the pin class we saw before. So really handy. It looks like you can do things like have an input with a pull-up resistor, so that's super handy for like reading a button or a switch. You can have the internal pull-ups on the chip. So that's really cool. Now something really neat is that it also has a PWM, a pulse width modulation class. And so this is really good for controlling an LED and changing the brightness of it. So like the PWM signal is like a square wave, that's on and off. And if you control the duty cycle, or how, the ratio that it's on versus off, then you can control the brightness of this LED, because you're basically turning it on really fast and turning it off, and then your eye kind of averages out how quickly it's turning on and off, and you see that okay, it's when it turns on and off half as fast, maybe it's going to be less bright as before. So let's try this out, and I was playing with it before. It's really nice, very easy to use. So there's a PWM class that you need to create, and so I'm just going to go and we'll do kind of like their example. So from the machine module, import pin and PWM into the global namespace. And now if I want to create a PWM object, I'll create LED PWM and create that PWM object, and then you have to pass it a pin, it looks like. So then you create a pin, and you don't need to set it as an input or an output, it looks like. You just give it a pin object. And in this case, pin 2, and even though I'd already set it as an output, I think this is going to change it so that it's an output again. Like if it was an input, for example, I'm guessing this would make it an output. So let's make a pin, and this is pin 2 that I'm using. So okay, so that's cool. And then with PWM, there are kind of two variables, or two things you have to tweak. There's the frequency, which is how fast that square wave changes. And you can read a little bit in here. It mentions that all of the PWM pins, so pretty much every pin on here, except for pin 16, it says, can be used as a PWM output, but they all share the same frequency. So you just need to be aware of that, your frequency is something that you can't control per pin necessarily. But you can have between 1 and 1,000 hertz, so once a second versus 1,000 times a second. And I think by default it looked like it was just using 500 hertz. So if I do LEDW PWM.freq, then this will tell me the current frequency it's using, so 500 hertz, which that's quick. Like my eye is not going to be able to see 500 times a second, so that seems to be okay. We'll stick with that. And then the duty cycle, you can use the .duty function to read it. And so 0 duty cycle, and the duty cycle here, they say it goes from 0 to 1023. So it's basically just a value, and if it's at 0, then it's basically a purely low signal. It's never above the 0 voltage level. Versus if it's halfway in between 0 and 1023, so if it's like 512 or so, then it's at a high level for half the time and a low level for half the time, which would average out to look like half as bright. And if I set it to 1023, then that just means it's going to be on for all of the entire waveform. So it's going to be full brightness effectively. So let's try playing with that. Let's do LED PWM dot duty 1023, and we should see it looks like it's just on, pretty much full brightness. But let's cut this in half and see what it looks like. So let's do 512, and oops, too many parentheses there. So you can kind of see it, and you might not be able to tell from the camera, but it dropped down a little bit. So let's go even lower. Let's go down to like maybe 10 duty cycle here. So it looks like it's off to you potentially, but it is a very little dim kind of brightness to it. So we can go like duty cycle of 200 maybe, and so now it looks a little more dim there. And you could have a loop in here if you wanted. So like if I want to go for I in range of 1024, because remember the range function in Python will go from 0 to the value you pass in -1. So if I want to go from 0 to 1023, I want to do a range of 1024. And then in here I just want to do LED PWM dot duty of I, and then let's just do a time dot sleep of like 50 milliseconds in here. So we'll let this kind of run, and then watch the LED. So it's kind of getting a little bit brighter, and it's slowly going up there. It looks like it's maybe a little bit over half brightness, and then now it's pretty much full brightness, or just about there for full brightness. So it's yep, looks like it's full now. And it's interesting. I'm noticing you might see some flickering in the camera view, but the LED itself is not flickering when I look at it. It's just some aliasing with the the video camera. I think it's recording at like 60 or 30 frames per second, and so you see some of that coming through as flicker for this. But yeah, it looks like this is working pretty well. And let's see, so it's still going. I think we're almost at full brightness. I guess it'll finish, the loop will finish once we're at full brightness. So we'll give it a second here to finish. But that's really handy. It's super useful to have, okay, so yeah, just finished there, to have very easy to use PWM functionality. You could also use this with a little piezo buzzer or speaker and do like really basic tones. It's not going to sound very pretty, but you could make, like high pitch, low pitch sounds, things like that. So useful to know about that. That's a very handy class to have. Now it also has the ADC, the analog to digital converter, and I won't play with it much. The only thing to note is that the ADC on the ESP chip, there's only one, and it goes from 0 to 1 volt. So you need to be a little careful about the signal you're passing in, and that you probably need to cut it down. Maybe with like some resistors potentially, or if it's a really low signal, you might need an amplifier to amplify it. But get some signal within that 0 to 1 volt range. It's not like an Arduino where there's an analog voltage reference that you can use to kind of change that. You're just stuck between that 0 and 1. So get your signal into that range, and then you'll be able to read the values. And it gives you values between 0 and, they say 0 and 1024, but I don't know if they really mean 1023, because that's not like that would actually be 1025 values, which you don't see a lot of ADCs like that. But in any event, it's not super precise, just 10-bit, but it's useful to have that ADC functionality. They also have SPI and I2C, and I haven't played with these yet. Maybe in a later stream might come back to some of these, but it looks like the basics are here as far as like being able to send and receive data over a SPI connection, and it looks like it's got everything as far as changing the polarity and the phase, like the different modes of SPI, the baud rate. Super handy to have that. Looks like it's really easy to use. Same thing with I2C, so it looks like it's got reading and writing from different registers on a device. So this will be really handy to write, different drivers to talk to, things like sensors, like an I2C sensor, or like I2C, like an OLED if you want to make a little display. So I think there'll be some really cool stuff we'll see in the future once, some of this stuff is kind of finalized and people can start building some of the drivers to control this hardware. They also have a one-wire driver, so you see this with a lot of temperature sensors. So it's cool, they've got it built in here. It looks like it's pretty easy to use. But the one I wanted to play with next is the Neopixel Driver. So this is really nice. It has a real simple, easy way to control neopixels. And so neopixels, they're little addressable red, green, blue LEDs. They just need one data line, and that data line is kind of chained around all the LEDs. So really easy to wire it up. And it's based on just having a very tightly controlled output signal that encodes all of the different bits of the color data as a certain signal, certain frequency that it changes. And so you don't have to worry about all that. You really just have to know how to control the high-level pixels, to set the colors of them. And I was playing a little bit with it, so I noticed that I don't know if the build I'm using has the Neopixel class included, because when I try to import it, I'm getting a module import error. But it does mention that the ESP module has a low-level function for controlling Neopixel. So maybe in the future this Neopixel class will probably be an easy way to use it. But right now you can actually use this low-level function. So let's give it a shot. It's in the ESP class, which I think I've already imported, but let's do this again. Import ESP. And then there's this Neopixel write function, and it takes in a few things. So you need to create a pin object and set it as an output, and that's the pin that your Neopixels are connected to. So let's do that first. We'll say pixel pin equals machine.pin, and mine are connected to pin 15, I think. Yeah, pin 15 on there. So we'll do pin 15, and I want to set this as an output because the signal will get written out to the Neopixels. And then what I need to do is I need to create a buffer of data to send to the pixels. And the way the Neopixels work, you send out, and for these pixels I believe the order is green, red, blue color data, and for each of those they have a byte. So there's a byte value for green, so that goes from 0 to 255, a byte for red, which goes from 0 to 255, and a byte for blue, 0 to 255. And so by changing all three of those, you can change the color to pretty much any RGB color. And so you need to make an array of 3 bytes for every pixel that you want to light. And the order of the pixels, basically the first 3 bytes will control the first pixel, the next 3 bytes will control the next pixel, and it just chains on all the way through all the pixels on there. So it's not as easy to use this low-level function because you need to create that buffer, but it looks like this Neopixel class eventually will have a really easy way to do this. So let's do it. Let's light up a few pixels here. So and the buffer object that you need to create, it's not an array that you can pass this function. You actually have to pass in a buffer object in Python, and I'll show you how to create that. It's actually pretty easy. So let's say my pixel data, and I'm going to create this as a byte array. And so this is the kind of magic buffer object in Python. It's basically a mutable buffer of bytes, I think is the right way to describe it. It just means that it's like an array in C, that you're used to, where you say, hey, I want 10 uint8 objects, like 10 bytes. And it'll give you, here's a block of memory that's contiguous with 8 bytes, and you can go wild on it. You can go in and change any of the values. That's effectively what the byte array does, because an array in Python is not like an array in C. An array in Python, I believe, is a linked list. So it's, you can add things on at the end, and it's not necessarily contiguous memory. And so that's kind of why you have, sometimes you need to have like a buffer object where it is like contiguous memory here. So that's the case with the pixel data here. So it's just something to be aware of. And luckily, the function will fail if you try to pass it in an array where it expects a buffer, and it'll give you a good error message. It'll say, hey, I expect a buffer. But it's sometimes not obvious if you're not used to that. If you see, okay, well, how do I make a buffer in Python? Buffer kind of, look at byte array. I believe there's also just a byte, or maybe it's a bytes class, which is similar to the byte array, but not mutable, which means you can't change it. That still might be fine in some cases, but in a lot of cases you want to be able to go back and change the data. So usually byte array is a good one to use. Now for the byte array constructor or initializer, you can either pass it how many bytes to create. So in my case, like let's light up 3 pixels. And so 3 pixels means 3 bytes per pixel, so I need 9 bytes total. You could even do like 3 times 3 here if you want. And so this will make a byte array that's 9 bytes long, and I think it'll even print it out if I just say pixel data, so we can see, yeah, like here's my byte array, and they all get set to a default value of 0. Now another way to create, and then once you have this, you can just go in like you're talking to an array and say, okay, pixel byte 0, I'm going to set to 255, for example. And then if I print it out again, now you'll see, okay, the first byte is OXFF. It's kind of printing out like a hex string here. So that's one way you can do it. Another way is you can actually, if you have an array of bytes or an array of values from 0 to 255, then the byte array initializer can take that in directly and it'll create the byte array using those values. So, I could just say pixel data equals a byte array and pass, now here's a Python array or list object, and now I can just pass in a list of numbers. So for my first pixel, and remember the order for these pixels is green, red, blue. So let's make this one red. So I'll say OX00, OX255, or OXFF, sorry, and then OX00. So that basically means green 0, red 255, or red maximum FF, and then blue 0, so no blue. And then for the next pixel, let's make this one green. So in that case, I want the first value, and you don't have to use hex. Like I could use 255, so green full value, red 0, blue 0. And then for the next pixel, let's make that one blue. So let's do 0, 0, 255. And then I want to close this list. And so now I have this, and then if I look at the pixel data, now you'll see it's kind of, just showing all the hex values for these. So that looks good. So okay, so now I'm ready to call this function. So it's the esp.neopixelWrite, and I need to pass in the pin object I created before, so I'll give it the pin. Then the byte array, or the buffer object, so we say pixel data. And then there's a last parameter, it's a Boolean that says, is it an 800 kilohertz or a 400 kilohertz set of neopixels? Most of them are 800 kilohertz, so this one is 800 kilohertz, so I'll say true. But if you set this to false, I'm assuming this falls back to 400 kilohertz then. So let's do that. And oh, look at that. Hey, look, red, green, blue pixels right there. So you can see how it set all the pixels on there, and it's pretty easy to set this data. And if I wanted to, I can go back and I can change this pixel data. Like let's set the first byte now to 255. Oops, I need to actually put an equals in there. And because I created a byte array, it's a mutable thing. I can change it, so I can do that. And then let's go back and let's just do the same write commands. We're going to write out the pixel data again, and now you see this first pixel turned into like a yellow kind of color because it's green and red mixed together. So pretty cool. And I mean, you could go wild with this. You can make a loop. You can animate things. You're writing out the neopixels effectively, so you can control lots of different neopixels from just the Python code in here, which is pretty cool because this is Python, so it's a little bit easier to deal with objects and things. And then the other cool thing is you've got all the Wi-Fi and networking support, so you could talk to a web service, pull down some data, parse the data, and then maybe get like a weather forecast and then change a strip of neopixels based on that. So really cool stuff you'll be able to do in the future with this. But it's awesome how simple they've made it to talk to neopixels. So neopixels and PWM, those were two things I wanted to show. And then let's come back to networking. So networking, this is how you can use the Wi-Fi on the microcontroller. And we'll see, I had a little bit of trouble with this, and I think it's just, it's all in development, so it's not really working fully for me. But let's just try it out, and I'll show you the error that I ran into, and we might be able to see if we can maybe figure out a little bit more of what's going on. So to use this, there's a network module that you want to import, so we'll do that. And then in the network module, it looks like it has a concept of there's a network interface that you need to create, and that's this network.wlan, like a wireless LAN. And then once you have that, you can go in and they have like a socket interface where you can make a socket connection to connect to a website and ask it to give you the web page, something like that. So first though, we need to create this wireless network interface. So we do network.wlan, and then it takes in this parameter here, which lets you control if this is if the chip should act as a wireless access point or as a wireless client. And this STAIF means that you want to act like a client, like you want to join a wireless network so that you can talk to the internet, talk to other things on the network. But it looks like it also has support for acting as a wireless access point, which is really cool. And you can actually see here, 3 lines. You just say, okay, create this WLAN, make an AP, here's the SSID to give it. I don't know if you can give it a password or not, but that's pretty cool. And then things could connect to your device. So that's really simple, really easy to do that. But let's connect to my Wi-Fi network here. So let's make a WLAN object, and we'll say network.wlan. and then I need to pass in kind of this station interface. So we'll copy that out, paste this in. And then on this WLAN object, so let's just use that dir command again, and we'll see. So yes, it's got like connect, disconnect, get the status. Let's just see what's the status. So let's call the status function. Oh yeah, so the status, this returns a value of like 5 or 4 or 3. Unfortunately, it doesn't give you a nice kind of string. You know, this is more of a code that you need to go and look up. And if we go into actually the reference here for the network module, which I think is further above, let's see, oh no, it's down in the MicroPython libraries here. Yeah, in this network class, you can actually see, so here's the WLAN object, and so it has a status, and so this kind of tells you, I think you kind of have to look at the code right now to see, but a value of 5 means that it got an IP address. And I think that's because I had previously connected it to my Wi-Fi network, and I think the ESP chip kind of remembers that, and so it's already connected itself to my network. But I'll just show you how to do the connection yourself. It's actually really easy to do this. So you basically just need to call this active function. So we say active true, and I think this just tells it to initialize and turn on if it wasn't on already. And then I want to call this connect function, and you just pass in your access point and your password. So really easy. So we'll say wlan.connect, and my access point, we'll say Tony 2.4, and then everybody gets to see my wireless access password. So there we go. And you'll see here there's a little bit of kind of debug output, or you know, there's like this FR0 and this like scan SCN1, something like that, or oh, scan done, I think it's saying. They probably missed a space there. But basically, that's just some debug output. And again, you know, it's beta firmware. You're going to see little things like that, but it doesn't matter. Just press enter and you'll get a clean prompt again. And that stuff, it's just output. It's not affecting the input. So if you're typing something and random characters come up, don't worry about it. But now let's just see wlan.status. We should still be status 5. And then they also have, oh, interesting, I'm not status 5. So I am status 1. Which means, oh, I'm connecting, so connection is in progress probably. Let's see what happens if I do this. Let's see, wlan. There's also an is connected function in here. So okay, so it says false. So let's see, it might have been in a weird state where I was already connected and I told it to connect again. I might have actually gotten it into a bad state. So let's say disconnect, and let's see if this gets it back into a good state. So okay, so interesting, it's telling me that it goes from state 5 down to 0. Now if I do wlan.status, now I'm in status 0, which that sounds like that's idle, so no connections. Okay, let's try this again. Let's do wlan.connect to Tony 2.4, and then the password. And let's see, so we'll, there we go. So now you see it's actually printing out some stuff. So it looks like it's like, here's some debug output where it's getting an IP address with DHCP. So that's cool. It looks like it's probably connected. So now let's see wlan.status. So now we're status 5 and is connected. Should be true. So yeah, I'm true. So okay, so cool. The chip is connected to my Wi-Fi network. So okay, so now to try out some of the socket stuff and the program and actual, you know, like talking to a web service. Let's see. Let's go back down to their library list. And let's go to, yeah, the network class, or yeah, here's the example, sorry, on this page already. So you need to import the socket class, and it's very similar to the socket class in Python. And actually you can see if you go to Python socket, and so you can see all the documentation. They've tried to make it very similar. It doesn't support everything that the Python socket class supports, but it's a good way to kind of wrap your head around it if you're not sure how to use the socket stuff. A lot of the functions are very similar as you know, they are in Python. So okay, so first you call getAddrInfo, and this is basically how you resolve a domain name to an IP address. And unfortunately, in Python, I actually think when you do a socket connect, you can actually just directly pass in a domain name and it will do this resolution internally, but it doesn't seem to be the case in MicroPython. You kind of have to do this yourself, but it's not hard. It's really easy. So we can just call, let's do my address equals socket.getAddrInfo, and then here you pass in the domain name, so let's say like adafruit.com, and then a port, so port 80, And then this will come back, and the adder object that's returned seems a little weird, but this is kind of by design. This is how Python does it. And so it's an array with a tuple inside of it, or a tuple, and there are multiple values in here. And I forget the meaning of all these different values, but the last one is the most interesting. This is the tuple or tuple. There are two values in here. There's the actual IP address, so this is the IP of Adafruit.com, and then the port again. And this is important because this tuple or tuple is what you pass into the socket connect function right here. It expects this exact set of values, so it needs the IP address and the port to connect to. So an easy way to get that is, and they do this in example code, so you can reference, because remember this is inside of a list, so I want the first item in the list, and then -1 means once I have this first item, which is actually this tuple here, grab the last element inside of it. That -1 means grab the one that's previous to the end, and so that's this tuple here. So if I press enter, you'll see that's the value that I get there. So that's what it means when you see in this example code. It seems a little funky at first, but they're just kind of parsing out this little tuple of values in here. So okay, so now let's call the connect function. Let's make a socket first. So say s equals socket.socket. So we're just creating a socket object, and then s.connect, and I want to pass in. Whoops! I accidentally pressed down. It's interesting in that I hit the mouse wheel on accident, and I guess OS 10 passes that through, or maybe turns it into an up and down key press in here. So okay, so let's do s.connect, and let's do that adder 0 -1 again. Oops. And then okay, so this is connected to the socket, and now I can do a send, and so this is actually just sending basically an HTTP GET. So like this is what your web browser does when it connects. And so unfortunately, they don't have built out yet like a web client class. I'm sure in the future someone might come along and add this because it's not too crazy to add on top of this. But it would be really neat if somebody ported the requests library, which is a really popular HTTP library from Python. If someone ported that to MicroPython, that would be really fun. But for now, you can kind of do it the manual way. So they make a little byte string here. And this B basically means, if I remember correctly, this means treat this as raw bytes, and so that like don't try and escape crazy things. I think that's what it means. It's been a while since I've used a lot of these strings here, but okay. So let's do s.write, and we'll pass in s.send, and we'll pass in this string that they passed, and so this is going to try and get the root of Adafruit.com's web page. And so we'll close that. Okay, so we'll do send, and it returns a value 41. I'm not sure what that actually means here. Like, actually, let's look at the Python socket write or send function in here and see what it returns here. So send the socket returns the number of bytes sent. Oh, okay, so it's just telling me how many bytes it's sent. Okay, so now in the code, in the example code, oops. I want to call this recv, receive, effectively, and you pass it how many bytes at most you like to receive. And so let's try this. We'll say data equals s.recv, let's say 1000. We'll grab the first 1000 bytes. And this is where I run into a problem, unfortunately. I get this OS error 104. And so this is basically throwing an error back. So something went wrong. Unfortunately, you don't get a nice error message right now, but I was digging through some of the source code, and basically it looks like what's happening here is, this is the MicroPython source code I'm looking at, and I'll just kind of show you too. Like if you look at their GitHub repository, it's very well structured. The code's very easy to follow. So the ESP8266 directory is kind of where they have all the code that makes MicroPython work on the ESP board, and then any ESP specific logic, things like that ESP class that lets you sleep for a period of microseconds and stuff like that. That's all implemented here. Now there's some common functionality because they have multiple implementations of MicroPython as far as like you can run it. The stmhal directory is for an ST32 microcontroller, which is what the original MicroPython Pi board uses. But it supports other platforms like just a bare ARM processor, something that might have like a CC3200 Wi-Fi chip. So lots of other platforms here, but some of these platforms share code. So like the ST32 chip shares some code with the ESP chip, and it's in the xmod directory where a lot of these shared modules live. And so the mod LWIP.c, this basically is the lightweight internet protocol, lightweight LWIP library that they're using. It's basically an embedded TCP/IP stack, nice open source project, so really nice that MicroPython can pull that in. They don't have to write their own IP stack because you don't want to do that unless you want to be chasing crazy bugs for a long time. So okay, so this is actually the code for this recv function. It's inside of here, and it's actually, if I search for socket recv, you can see this is actually the C code that's being called, because MicroPython itself has to be implemented in C, at least most of it, because it's calling C functions, you know, and it's more efficient to do it in C. So this is basically a C function that gets exposed in Python. And so inside of here, I won't go through all the code, but basically if it runs into an error, I think it's failing right here. So it's calling this LWIP TCP receive function, and then for some reason that's failing, so return code of -1, and then it raises, you can actually see this is where it raises that OS error, and then what it's passing into it is this error number, and so that's what this value is here, this 104. So you can see the OS error. So 104, so if I go back, so now I need to figure out what is error code 104. And if I go back up here, you can actually see near the top of this, they show a mapping here of error codes, where they're basically mapping from standard, I think it's like a Linux or maybe a POSIX standard for error codes. And that's actually what the socket libraries itself, like the LWIP library, uses. And let's actually look at the LWIP error codes, because I found this in their GitHub repository, or rather, let's look at the LWIP code. And this is actually a clone on GitHub. Somebody just took their repository, because they actually have a Git repo on a different website, but I think it's a little easier to use GitHub's web interface, so I'm just going to use this. And let's look at error numbers. Let's search for error numbers. And I think they actually implement in LWIP a header in here, if I remember correctly. I think this architecture. Yeah, so here we can see these are all the error code values. And so 104, so we're getting a connection reset by peer error number here. So this basically means whoever I was talking to probably closed the connection, which is interesting because I think I was getting a different error before. So I have a feeling what happened here is that I ran this connect, and then I ran this send, and it took me a few seconds to make this send. And then it took me a few seconds to actually do this recv command. So in that time, the server that I'm connected to probably said, you took too long, I'm just closing this connection. Because when you run a real web server, you need to worry about like denial of service attacks, where someone opens a connection and then they very slowly send you data, and that'll tie up maybe a thread if your server uses threads. And if you do that a lot of times, then suddenly your server is overloaded, and you've got all these slow connections. So a lot of times servers, if you don't respond within a certain period of time, they just close the connection and you're done. So it's a little tough to use it right now. But from what I understand, there's also a file system you can create on the board, and they don't have a lot of good examples for it, so I don't have any examples of how to use it yet. But from what I understand, eventually, like I think right now, if you take the MicroPython source code, you can actually add your own .py files to it. So you can explicitly add Python scripts that get compiled into your firmware, and then you burn that to your chip, and you've got your code that's ready to run. But I have a feeling they're going to work on letting you dynamically create files and things like that. So it's not there yet. So I won't go into this yet. But basically the socket functionality is there. It might be a little tricky to use it in this kind of interactive window, but maybe something to play with more in the future here. So, but also just good to know, when you get some of these weird random errors, there's maybe not as useful error codes yet inside of here. So if you get something like this OS error and you're calling the socket functions, go back to the LWIP code here and look for that error code. And I think these are even just standard across almost all Unix systems. So like if you just search for errno.h even, or it looks like there's a man page in Linux. Let's see, oh, this one's bad. Search for erno.h, because this is usually what you include to get all these values. And so if I go down here and if I look for the value 104, So we say, okay, so it is good. So it's the same. So econ reset, so connection reset. So another way to look up these error codes if you run into them is just, search for error_node.h and you'll be able to find them there. So, okay, so that's cool. And then a few other things I just wanted to mention. So there are some other libraries that they have. They have these little micro libraries, they call them, where they've basically taken some very useful standard Python libraries and made them small enough to run on little embedded chips like the ESP32 or the ESP8266 chip that we have here. So the one useful class that I think is really cool, they have a Json encoding and decoding library. And if you've ever tried to talk JSON from like an Arduino, you're tearing your hair out because you're trying to do parsing of like, dynamic strings. And it's pretty complex parsing with JSON. There's context dependencies, you've got dictionary-like objects and arrays, and it's not pretty. It's not the kind of thing you're just going to write in a sketch and make it work. You're going to need to pull in a library to do that. But hey, MicroPython has done all that hard work for you. They've got this in here. So let's play with this. Let's import the UJSON. So U, I'm assuming, means micros, like microJSON. UJSON. And then here you just have two functions. So if we look at the microJSON module, just dumps and loads. And this is just like the Python JSON module. But the Python JSON one has all these extra parameters for like you can change the formatting, and I doubt you have that level of capability here. Basically you can decode and you can encode things as JSON. So dumps is how you encode a Python object into JSON. And so like let's make a foo object that's a dictionary, and let's give it a bar value or property, and let's set this to 42, and then let's say baz, and let's make this an array. So let's say 0, 1, 2, and then we'll close this. So this is just a Python dictionary object. It's got a few different properties in here, and then I can just pass this directly to the ujson.dumps, my foo object, and this is cool. So this gives me back a string that is JSON encoded. So if I'm talking to a JSON web service and I need to create some crazy parameters, just create them as Python objects called dumps and then send that string off to them. And if you want, you can also decode the response. So there's ujson.loads, and let's just pass it in directly this string right here that we encoded, and we should get back the object that we encoded. So there we go. It returns back a Python object. So this is pretty cool. Like, I think combine this with the networking code, talk to a web page, call a web API, send it some JSON data, some parameters, get back a JSON result, parse it, pull out the value that you care about, talk to your hardware, maybe control some Neopixel, something like that. And in fact, I was just thinking, the little Twitch on air sign that Lady Ada did in quite a few streams back basically has, it's using an ESP8266, but it's using the Arduino code, and it's it's not actually as advanced as parsing all the JSON code, because Lady Ada kind of saw that you don't actually have to parse all the code. You can actually just look for the presence of a certain value, which that's the kind of trick that you usually end up doing in Arduino and C code. For this, you don't have the luxury of being able to parse that JSON. But here with MicroPython, we're running on this ESP chip that has a lot more memory, a lot more program space, so we can just decode JSON and encode it directly, and you're good to go. So I think we could probably eventually build the Twitch streamer purely in MicroPython. Once I need to play more with the networking, and I especially need to play more with the file system and figure out, how to write a script and have it run, automatically on boot. And then hopefully that'll be able to talk to web services and not get all these connection resets and things like that. But it could just call the Twitch API, get back the JSON data, parse it, and output stuff. So that's pretty darn cool, I think. It's something that I'm definitely looking forward to. And I think this will be really useful for things like physical computing and just being an easier entry into talking to hardware. You'll be able to program stuff in Python here. So really cool thing to look at. And maybe let's take a quick look and just see the other libraries they have here. So they have bin Ascii Library. This is a really handy library in normal Python. It's a good way to like print out like the hexlify function is one that I use all the time. Let's see if they have it. Oh, good, they do have it. So if we import ubin Ascii, then I call ubin Ascii .hexlify, and if I pass it a list of bytes, like actually the pixel data that I had before, this will actually just print out like a nicely formatted hex string of the values. So like that, these are the Neopixel bytes that I sent before. So good for debugging. Like when you're looking at, I've got some array of bytes, what's actually in here, bin ASCII.hexlify, super handy. It looks like it actually has the inverse too, which is really cool. Like if you get, I don't know, maybe you talk to some crazy web service that gives you back just a list of hex values. Very easy, one-liner right here to convert that into actual bytes. So that's cool. C types, this is really neat. So C types is basically how Python code can dynamically talk to C functions and C code. And you do that by building up Python objects that are compatible with C structs. So like a struct in the C language is an object, quote unquote, or it's a bunch of values that are all associated with each other, but they're all in the same spot in memory, and like sometimes they're aligned in certain ways. But it's really important because if you have a dictionary object in Python, it's not like a structure in C. It might be all over the place in memory, versus if you want to go call a C function that expects a structure, it expects everything to be in the same spot in memory. So you need to use C types a lot when you're dealing with C functions. And because MicroPython itself is built on a lot of C extensions and things, it makes sense that they have their own little C types library here. So I'm guessing this is a useful way to marshalling is sometimes what you hear as far as like taking data that's in the format for Python in memory and converting it into the format that like C would expect in memory. So super handy, very cool that they have that. It looks like they have a hashing library, so that's kind of cool. I'm guessing this has some basic hash functions in here. So yeah, it looks like not a ton of details in there. Heap queue algorithm, that's pretty cool. This could be useful for, if you're doing, I don't know, like queue, like priority queue things, maybe something like that. Push things on potentially. And then the JSON library looked at. Regular expressions, this is pretty cool. Again, something that in Arduino, total pain and agony if you ever wanted to do a proper regular expression. Now it doesn't look like this is as complete as the real Python regular expression library, but it looks like you're pretty darn close. I mean, you can do things like pattern matching, you can capture things, it looks like you can you can say here's like how many repetitions I want. So very, very handy again for parsing. So like if you're talking to some web service and maybe it's not JSON formatted, maybe it's some really gnarly format, maybe a regex will work. But you can also get down the deep rat hole of, sometimes you're trying to build a regex for something that you really can't build a regex for, so you create a lot more problems. And then they actually have zlib, so like zip compression, which that's pretty cool. So if you want to decompress something, I'm guessing this might be handy. I don't know if it does it internally, but like some web servers you talk to will give you gzipped data back, and so you need to like convert that, and so it's handy that they have this library here. So it kind of looks like all the things are starting to come in together, all the pieces are starting to get there to make the MicroPython and the ESP8266 a really powerful little platform for Internet things. You've got a lot of different little web-related APIs and things, handy functions like JSON parsing and encoding, that it'll be really easy, hopefully, to talk to web services. So it's early days, though. You don't have something as nice as like the requests library in Python that makes it really, a couple lines to talk to web service. But I think over time, you're probably going to see stuff come that, it's maybe not exactly as capable as those libraries, but comes pretty close and makes it much easier to do that. So I think I'll probably end the stream here for this. If people have questions, maybe throw them in the chat, and I'll scan it real quickly. We'll take a quick look and see. Let's see, let me change back to kind of the main view here. So, and let's see. So yeah, I don't see any questions in chat. So yeah, so thanks a lot for watching. Let's see, the next stream I do, so I'll do a stream on Friday. I'm back to the normal kind of Friday time. So Friday last week, I started a new series of talking to things from a Raspberry Pi, or talking to little Wi-Fi boards. And so if you didn't see it, you can go back to the YouTube channel, youtube.com/Adafruit, and see the first video in the series where it was kind of showing how to take an ESP8266 and have it send sensor data to a Raspberry Pi and log it to a file just using some built-in tools like Netcat, a really handy kind of Swiss Army knife of network programming. So real cool, good intro stream. So this Friday I'll do another stream. We'll do a follow-up and do kind of part 2 in that series. And so I'm hoping to kind of slowly build on that, and maybe start with doing some simple socket programming in Python, so that maybe let's build a little Python server to do kind of the equivalent of what we did in the last stream. And then Monday again next week I'll do another stream for something. Usually I like to look at kind of software. I don't do as much programming in the Monday streams. So like I was looking at MicroPython in these last 2 streams. I think I'm probably done with MicroPython for now. Let's let things kind of mature, and we'll come back to it and see how things are going, maybe in a few weeks or so. But yeah, so tune in to youtube.com/Adafruit. You can see this video, all kinds of other fun projects. Subscribe to twitch.tv/Adafruit. You can watch me stream this live, interact, ask questions, stuff like that. And we're also starting to do a lot more stuff like Facebook Live. We're starting to stream there. So, pretty much, I just read today actually YouTube has live 360 video streaming, and I'm not set up for that. But Phil and Lady Ada, they might be potentially in the future do some 360 streaming. They've already done some 360 streaming with Hug VR. So really cool. We're trying to push the boundaries of live internet here. So thanks a lot for watching, everybody. Like, comment, subscribe, do all the fun stuff there. And I'll see you guys Friday. So we'll do part 2 in the Raspberry Pi Talking to Wi-Fi Things series. So that's it. I'm Tony from Adafruit, and I'll see you guys Friday.